The first thing I want to talk about is random error. Your percent sulfate in all your unknown samples should be the same, but normally they aren't because there's going to be some fluctuations with random error. So random error can be eliminated in theory. When we have random error, let's say there's a true value. We don't know what the true value is, but let's say the true value is here. When we take our measurements, some measurements might be right on. Other measurements might be a little high or a little low, depends. But if we take an infinite number of measurements, what we're going to do is we're going to build up a distribution of measurements. This. And the further we get, the larger the error is, the smaller the population of measurements. Most of the measurements are going to hover around the true value here. That is, if there's no systematic error. If there's a systematic error, like say a miscalibration, then the whole thing could be shifted one way or the other. And so in theory, if we have an infinite number of measurements, then our expectation is that 50% of them will be too high and 50% will be too low. And the random error cancels. But the problem is we can't take an infinite number of measurements. But let's talk a little bit about statistics. There's something called the standard deviation, and the standard deviation we could figure out for this population is going to be like this. This is supposed to be the same on both sides. I don't know. Let me try to fix that. So if we're plus or minus one standard deviation, so this would be plus one standard deviation. And this would be minus one standard deviation. Then the statistics say that about 67% of the measurements will lie within plus or minus one standard deviation, and then 33% will lie outside this standard deviation. So we call this a confidence interval. So this is called the 67% confidence interval. (67% confidence interval). And that just says the 67, well, we'll talk about it later in this. Normally what we do is we don't have an infinite sample size. It's not that important. You don't have to know this for anything. So we don't take an infinite number of measurements. Let's say we only take 3 measurements. So if we take 3 measurements here, random error is going to say that some measurements are too high, some measurements are too low. But if we take this, how can we estimate what this distribution looks like here? And so it depends on this. It's going to depend, our confidence, let's say, depends on 2 things. The number of measurements and 2, the spread. The spread would be like the smallest and the largest. How wide is the spread of values? Otherwise known as precision, So if we take 3 measurements and they look like that, that's fine. Or what if we take 3 measurements and they look something like this? Which has a much wider spread. Then you'd expect the distribution to be a lot wider here. And we're looking at the plus or minus 1 standard deviation here versus plus or minus 1 standard deviation here. And you can see that the standard deviation is going to be much larger in the second grouping. Or if we take 2 measurements versus 1 measurement versus 1,000 measurements. And so the number of measurements is going to have a large impact here. I mean, if we only take 2 measurements, it looks as if the spread is a lot narrower, but it actually ends up widening the spread because we can't have as much confidence. So when we look at the standard deviation here with 2 measurements, the standard deviation is going to be a lot wider. And so the more measurements I take, and the more precise they are, the narrower my standard deviation is, I lost the top half of that. Let me fix that. I forgot to insert pages here. So what statisticians have done, and this is what we're going to do to analyze it, a 67% confidence is too narrow. In science, it's standard. 95% is standard. If I had an infinite number of measurements, then this would equal the 1.96 standard deviations. So about 2 standard deviations. So what that means is that within 1.96 standard deviations, or in other words, plus or minus about 2 standard deviations, I would capture 95% of my points. So 95% of the area under this curve. Here. And that means there's only a 5% chance that it lies outside the curve here. So 2.5 on this side, 2.5 on that side. So that's an infinite number of measurements. But what we have to do is, if we have a finite number of measurements, that is, you know, not an infinite number, we have to make an adjustment to it. And so what we do is we call it lambda 95. Or lambda 95 is called the 95% confidence interval. And the way we use it is like this. Well, actually, before I talk about the way we use it, this depends on the number of measurements and the precision. The precision, we're going to look at the standard deviation. So if the standard deviation is very wide, then the precision isn't so great. And if the standard deviation is very narrow, the precision is much better. And so we'll be looking at those two things. So let's do an example. This would be a statistical analysis of random error in a population. Let's say I have 3 percentages here. And I'll try to keep the numbers simple. Let's do 67% was a trial 1. Then trial 2 would be 68%, and then trial 3 would be 69%, something like that. So we're going to do a number of calculations. The first calculation we're going to do is we're going to calculate the mean, the average. So the average is just, you just add them up and divide by the number of measurements. And so the average is just equal to the sum of the trials divided by the number of trials. And so this is just 67 plus 68 plus 69 divided by 3 trials. And that's going to give us what percentage? 68%. All right, this is the first thing we'll calculate. The next thing we're going to calculate is the standard deviation. So the standard deviation, there are different equations for standard deviation depending on if you're looking at finite versus, let's say, infinite sample set or whatnot. And so let me give you the standard deviation. Did I do that? Of a finite set. I get my Post-it. I'll have to give you the formula. This way. We're going to label it S, and there are different labels for this, S and sigma and whatnot, and again, there are different ways you can calculate this, but the equation we're going to use is for a sample. So let's say I better put that here. It's going to be sample standard deviation. Sample meaning a finite set of data. In the finite set of data, you're going to take n number of measurements, and then what we have to do is we have to subtract 1. It's going to be n minus 1. This is called degrees of freedom, and we lose 1 degree of freedom. That is, we took 3 measurements, but we're going to do 3 minus 1, which is 2, because of the average. We lose a degree of freedom for the average. And then we're going to sum this up from the first trial to the nth trial, and we're going to take the measurement from the trial 1 or trial 2 or trial 3, we'll just call it xi, minus x bar. X bar is the mean or the average, and then we're going to square this, because sometimes we'll have negative deviations and positive deviations, and we don't want the negative and positive to cancel one another out, and so we'll have to square these. And then we'll take the square root of this. And so we're going to look at the square of the deviations here. This is my x bar here. And this would be my x1. This would be my x2. And this is going to be my x3. All right, so let's go ahead and calculate it. This is going to be 1 over n minus 1, which is 3 minus 1. And then the sum of x1. x1 was 67%, minus x bar, which was 68%. And then we'll square that. Plus, the next term will be 68%. Those are x2 minus x bar, which is 68%. We'll square that. Plus 69% minus the 68%. So we're looking at the sum of the squares of the deviations, and then we'll square root this whole thing. We've got to square root the entire thing. So let me do this to the 1/2. So your numbers won't come out like this, I would imagine, but it'll be 1/2 times, okay, 67 minus 68 is 1 squared. It's just going to give us 1. The first term is 1. Plus, the second term is going to be 0. And the third term is going to be, this was minus 1 squared. This is going to be plus 1 squared. This is going to give us 1 here. And 1 squared is 1. I better just square this here, so you know. So that's going to be 1 plus 1 is 2, divided by 2 is 1, to the 1/2. And then we'll figure out what's the square root of 1. Does somebody know? Come on. 1 square root. Square root of 1 is 1. I should have known that. Okay, so 1 times 1. Right. All right, that's our standard deviation. Okay, this should be about the 67% confidence interval for an infinite data set, but we don't have an infinite data set. So the next thing we're going to do is we're going to do lambda 95. Now, our lambda 95 equation is going to look like this here. I'll give you the equation. it's going to equal T, and T is going to depend on two things. T is going to depend on, just do nu 0.05. S divided by square root of n. This factors in the number of measurements, n, and the precision of the, well, n, it actually goes beyond n because there's t. T also depends on the number of measurements. And s, the standard sample standard deviation. So let's take a look at t first. T comes from statistics. It's called the student's t distribution. Let's see. I need the table. Students' t distribution is not for students. It's for everybody. I think the mathematician was named student, so it's a little bit deceptive. But let's get the actual table here. I thought that was the actual table. Let's take a look at this. You get the, okay, this is going to give me this is, sorry, this is, I should have grabbed it earlier. I thought it'd be, it's usually easy to find. Students' t tables are everywhere. We'll just use this one. The resolution isn't that great, but can you read it okay, or actually, let me see. Oh, this is better. I'm going to copy this from Statistics for Dummies. I'm going to paste it into my document here. If I can. It's going to allow me to paste it without going to the top. Yeah. All right, so T depends on the P factor, which is the statistical P factor. And yeah, the number of measurements here. The P factor goes like this. So if you see a P factor of 0.1, that's a 90% confidence interval. A 0.25 would be a 75% confidence interval. A 0.4 would be 60%. So this is 60%. 75%, 90%, 95%. It's 1 minus the P factor times 100% converted into percentage. And so this is our 95%. In science, we usually use 95%. In other fields, like social sciences, they might use, other confidence intervals, like a 60% confidence interval over here. Actually, this is not quite right. This is only doing one side of this. Let me get a different, you have to be careful with these tables too. Take a look at if we go to 95% and we look at one measurement, it's 6.31. That's only one side of this. We need both sides of this. we can multiply by 2, but that's one option. I don't want to multiply by 2. I just want to read it off the chart. I mean, it's not hard to multiply by 2, but I would rather just read it. I can't believe, sorry, I thought it wouldn't be so difficult to find a decent chart. This is the same. I'll just show it from my book. All right, like you could have doubled it, but anyway, if we only take 2 measurements, do you see the T factor here is quite big? If we go from 2 measurements to 3 measurements, look at what happens to the T factor. It goes from 12 all the way down to 4. So what that means is that the bigger the T factor, the greater the uncertainty you're going to have. And so if just by going from 2 measurements to 3 measurements, we've reduced the uncertainty by 3-fold. Do you see that? And so it's a huge improvement. So if you have a choice between doing 2 trials versus 3 trials, 3 trials statistically is much, much better. How about if we go to 4 trials? Do you see a big payoff in going from 3 trials to 4 trials? It's not so big. So if the experiment is kind of complicated, we'll stop at 3 trials. Here. If we go on, obviously, if we take an infinite number of trials, we'll narrow it all the way down to 1.96, which would be the 95% confidence, but we're not going to do that. And so what's going to happen is taking a finite number of measurements is going to reduce the certainty and increase the uncertainty in the measurement, and it depends on the number of measurements here. This is for 95%. You know, if we widen the window, or that is, if we only go to a 90%, then we can see a little narrower to capture more of the points. And so the way we'll do this, we'll go ahead and use our T factor for, okay, this is degrees of freedom. And so we have to be careful here, because some of these do it by degrees of freedom, others do it by number of observations. So be careful here, because take a look at this T chart here. Do you see this one does degrees of freedom? Degrees of freedom usually have to reduce the number of measurements by 1 because of the average. And so it's kind of confusing at times because this is actually two measurements here. And then you have to decrease it by 1 to get the number of degrees of freedom. So 3 measurements decreased by 1 is 2. Versus this. I prefer this chart too because this chart just tells me the number of measurements. I don't want to calculate the degrees of freedom, although it's an easy calculation. You just subtract it by 1. Right? But it gets confusing because some charts are degrees of freedom, other charts are number of measurements, which is a pain. And so sometimes people use the wrong number because they accidentally use the number of measurements rather than the degrees of freedom, or vice versa. So here, this is a lot easier. There's 2 measurements, 1 degree of freedom, 3 measurements, 2 degrees of freedom, but I don't want to deal with that. Why do an extra calculation? So anyway, if we do 3 measurements, we're at 4.303. That's our T factor. If you do 2 measurements, it's less. So another reason I didn't like this table. So I'm going to eliminate this table from this here. I'll eliminate this table too. Here. This is also in degrees of freedom. So again, 0.05 means 95. That's our P factor here. So T is equal to, just reading it off the table, 4.303. This is going to be N. I'm going to change this from U to N. N equals 3, and P equals 0.05. Sometimes they'll do it by P. Actually, most tables will do it by P rather than just say 95%. It'd be easier if they just said 95%, but it's just because of statistics. P is very common in statistics. All right, so we'll just put in 4.303, and then we'll put in our standard deviation, which is 1%. I put my units on the standard deviation. Forgot to put my units. Forgetting the units is bad. So this would be percent squared, and then we square root it and get percent. And then we're going to divide by the square root of 3. And so I'm going to go ahead and punch that in my calculator here. 4.303 divided by the root of 3. 2.48. Do you see it's much wider than even the standard deviation is not correct. This plus or minus 1 standard deviation is for an infinite data set. If I wanted the 67% for a finite data set, it would be wider than 1%. All right, so how do we use this? Well, the way we use this is normally what's done with random error in averages. Whenever we report an average, we want some kind of statistical idea of the confidence that we can have in the average. You know, 2 people might get the same average. In this particular instance, the average was 68%. We include the 95, so it's going to be the average plus or minus lambda 95. And so we had 68 plus or minus 2.48%. And then we'll just do it to the same number of decimal places. So this is going to be 68 plus or minus 2%. It's It's actually 2.4. Maybe I'll subscript the 4 here. It's not, because there's uncertainty in the 8. So what this means is that the way we interpret this is that we should have 95% confidence that the true value, 95% confidence that the true value lies in this range. The true value would be, if we took an infinite number and then eliminated the random error, it would be the true value. Lies in this range. And so that would be between 66 and 70%. So normally when we report an average, we want to know, if somebody got 68% and they had, let's say, a confidence interval of 0.2%, then that's a very narrow range, versus if somebody got 68% and had a confidence interval of 20%. There's a huge difference in these two averages. So normally when somebody says, my average was 68%, well, you don't know how much confidence you can have in that. Is it very narrow like this, or is it very wide like that? And so this is why we report the 95% confidence interval, and this is what you're going to have to do for the sulfate lab. You'll have to report that. Okay, any questions on this? We're going to go into the computer lab next week. Next week we'll probably do the calorimetry graphs and the graphs for Wednesday's lab. I think I have it scheduled for Monday. So actually, today's experiment is fairly simple. But I need to catch up with light a little bit here. So we were talking about the visible part of the spectrum. What the visible part of the spectrum does is it excites electrons here in matter. And when we excite electrons, it causes some colors of light to be absorbed. If no colors of light are absorbed, that is, we don't excite any electrons, then the material appears white or transparent. If all the colors are absorbed, then the material appears what color? If all the colors are absorbed, do you know what color it appears? Black. We call things that absorb all colors of light, all colors of the rainbow, black bodies. So black bodies will absorb all these. All right, then we're going to move up to ultraviolet. What does ultraviolet usually do? Well, ultraviolet usually causes damage to things. What's that? Yeah, causes damage to different things. Ultraviolet, what do they do? Like some people carry ultraviolet lamps with them. Have you seen those portable ultraviolet lamps? To kill viruses and other stuff. Like they'll go to a hotel and then hit the ultraviolet, hopefully kill any bed bugs or whatever viruses might be around. But what it does is it breaks bonds. X-rays, you know what they do? X-rays can ionize atoms and molecules. And so ionize means knock the electrons off. When we break the bonds, it doesn't necessarily knock electrons off. You know, you just break the bond. And then gamma rays are also ionizing. So X-rays and gamma rays we call ionizing radiation because they can ionize matter. So we use different ways to protect yourself from ionizing radiation. Do you know what's most commonly used for protection from ionizing radiation? Lead. Why lead? It's not the protons we look at. It's the electrons that we look at. When we look at lead, how many electrons does lead have? 82 electrons. And so if the light is interacting with electrons, then lead is going to be good. But are there things that are better? What has more electrons than lead? Yeah, like radon, but radon's a gas. Polonium. You could use polonium. But what's wrong with using radon and polonium? They're radioactive. And so bismuth is there, but bismuth isn't so plentiful, not like lead. Lead is much more plentiful. And so what we have lots of electrons to absorb electromagnetic radiation. I'm sorry? Yeah, it's harder to ionize, right? I mean, it could ionize the lead too, form lead ions on the surface, but they're unstable though. But since it has so many electrons, it's good at absorbing. It's like black bodies. You know what color lead is almost? Lead is almost black. When you look at it's not like, there were some samples of lead. You know, you had zinc. Zinc had that kind of silver luster to it, but the lead had the kind of that dull black color to it. But anyway, lead is good for shielding. Ultraviolet, I mean, you could use lead to shield yourself from ultraviolet, but lead is toxic. It's a heavy metal, so you can use other things to shield yourself from ultraviolet. Ultraviolet is a lot less penetrating. Gamma rays are the most penetrating radiation, electromagnetic radiation. And so normally for gamma rays, we need lead brick. If you want to protect yourself, build a lead brick wall. For X-rays, we just need lead sheet. Because it's not as penetrating, not as energetic here. So we have relationships here between frequency and wavelength. They're inversely proportional to one another. And so frequency, wavelength, and speed of electromagnetic radiation. Frequency is in hertz or cycles per second. Wavelength is usually in meters, but nanometers are very common, and micrometers or microns are very common. For X-rays, angstroms are quite common. So you'll hear people talking about what wavelength in angstroms their X-rays are. What else is in angstroms? Do you know what else is in angstroms? Atoms. Atoms. So atoms and X-rays are about the same. And so they can interact with one another. But when you look at atoms and let's say ultraviolet, doesn't really interact, but we'll talk more about this later. This is not important now. What's important, you should know, atoms and X-rays interact. Where there's certain things that are invisible, that aren't seen. So you could see atoms with X-rays, but our eyes don't see X-rays. We can see visible light, but visible light is, well, it could be. It's more complicated. I probably shouldn't talk right now about it, but I'll talk about it later. So this is the equation that relates speed of light. Speed of light we usually just do to 4 sig figs, 2.998. This is enough for, so I'm going to round the 7 up by dropping the 9, times 10 to the 8 meters per second. And so from this we can calculate this is the speed of light. Nu is our frequency in hertz, and lambda is our wavelength in meters. The energy of the light depends on 2 things, which I'll talk about here. Let me insert a slide. It depends on the amplitude of the wave, which is the total energy. And it depends on the wavelength or frequency. The wavelength or frequency, this tells us the what we call the photon energy. The photon energy is given by this equation. E is equal to h nu, which is equal to hc over lambda, since nu is c over lambda. This is where h is equal to 6.626 times 10 to the minus 34 joules times seconds. And this is called Planck's constant. Planck's constant. The total energy, which we'll call E total, this I'm going to call E photon, is just the sum of the photon energies. It depends on how many photons you have of light. A photon is like a particle of light. And so what we see here is that the energy increases as we go right to left. This is increasing photon energy, which is equal to h nu. So as the frequency goes up, so does the energy. And as the wavelength goes down, so does the energy go up. On the bottom here, this is the photon energy equation. H nu, which is equal to hc over lambda. I think we'll talk about the solar spectrum now. I'm going to just take an image off the internet here. Hopefully I can find a decent.
We'll have to memorize Planck's constant and speed of light, right?
No.
Oh, you'll give us that?
Yes.
Oh.
You don't have to memorize the constants. I'm going to take this image from sun, wind, solar here. I'm going to use that. So here's the reference. Whenever you use something off the internet here, make sure you cite the source. So for your papers, if you find something interesting, include the source of that. So the visible spectrum goes from 390 to 760. And so this is the visible. And we usually memorize, let's see, this is going kind of backwards because we're going from higher energy to lower energy. The longer the wavelength, the lower the energy. And so if we go backwards here, it's going to be red, orange, yellow, green, blue, indigo, violet. So this would be it. When you look at the spectrum, it also emits a lot, like 1,000, 1,500, 2,000. What kind of light is this? Here's red, and what's on the other side of red? Infrared. So this is infrared light, and so you can see the sun emits some infrared, and you can feel it. Like in order to detect infrared, you just stick your hand in sunlight. When you stick your hand from shade to sunlight, do you feel how much warmer it is? When you're in shade, it's not because the air is warmer, it's because you're being hit with infrared radiation, because the air is cold in the shade, but when you go in the sun, you're hit with this. And you can feel it in your body. Yeah, then there's those, have you heard of the red light therapy? No, there's people who are using some of this. I forgot what wavelengths they use. It's in the infrared to stimulate your mitochondria or something like that. And then we have our visible. And then what's this? On the other side of violet is ultraviolet. And so this, because we have ultraviolet, they have ultra UVA, B, C, depending on how far it is away from violet here. And they have different parts of the spectrum here. They can do different things. But we got to watch out. Because ultraviolet, what does ultraviolet radiation do? It breaks bonds. And your DNA has carbon-carbon bonds. And so your bonds can be broken by ultraviolet radiation, and it causes damage. That's okay, because this is, when I took biochemistry, which is like decades ago, I remember this. The professor said that your DNA is cleaved, that is, the bonds are broken about 200 times per day. But it's not a big deal if it's in your skin, because your skin has repair enzymes, and the repair enzymes go and try to fix the DNA damage that's caused by the ultraviolet radiation. But now it's probably worse because of the ozone depletion, so we probably got a lot more than 200 or a couple of hundred DNA cleavages per day, so sunscreen's important. But it's about 5% ultraviolet, about 42% visible, and 53% infrared in terms of energy output. You know, the intensity here is going to show you how much output there is. And so we have things like, this is called the emission spectrum of the sun. Parts of the emission spectrum are missing. Do you see these gaps here? The gray is kind of the energy density, but the actual emission spectrum is this red. And you see these gaps here. And when we look at the gaps here, energy absorbed by water, vapor, and atmospheric gases at absorption bounds. And so what happens is infrared, what does infrared do to water? It causes it to vibrate. And then the water can actually only vibrate 3 ways. It's kind of weird. And it's based on the theory, and the theory is quantum mechanics. So we can use quantum mechanics to predict the vibrations of water. Let's take a look at the vibrations of water. These are called vibrational modes. I need to get rid of this. I can't go full screen. So this is one vibrational mode. This is going to absorb a certain frequency or certain wavelength or frequency of energy. Let's see, what was is that it? No, it's kind of slow. Let me speed this up. This is another vibrational mode. And this is going to absorb a different energy. There's not an infinite number of ways we can vibrate a water molecule. There's only 3 ways we can vibrate a water molecule depending on the shape of it. And so this is yet another vibration. Each of these vibrational modes absorbs a specific amount of energy. And it's fixed. It just doesn't absorb any energy. It just absorbs these. Okay, what happened? So we can see that here. One of those will be here. Another one will be here, a little lower in energy, and the third one will be here. And so there's 3 what we call absorption bands for water. And so when we look at the let's look at the infrared spectrum of water, because that's in the infrared region. We call it a spectrum. How light interacts with matter we call a spectrum when we quantitate it. So there are 2 ways we can look at it. One way we could look at it is upside down. Another way we could look at it is right side up. Let's see. So this is the infrared spectrum. So there are 3. This one's the most intense. So this is the most favorable vibration of water. And this is going to be at longer, this is frequency. So this is higher frequency, higher energy. So this is a higher energy, and then there's a smaller one, and then there's one over here with this little shoulder. But these are the ways the water vibrates. And that causes these absorptions. And so these we call absorption peaks here. And so these are the frequencies of radiation, electromagnetic radiation that are absorbed by water. So what happens is you could try heating up your water with this wavelength of infrared energy, and it's invisible. The radiation just passes right through water. It isn't absorbed. It won't do anything. This is why, when you heat up your water on the stove, you're exposing it to a whole spectrum of energies from the flame, because the flame is going to emit, if we look at the flame emission for infrared, it emits pretty much all the wavelengths of infrared, but only 3 of those are absorbed. So much energy is wasted because it's invisible to those energies or frequencies of infrared. And so much energy is wasted. So what if you just hit it with this? If you hit it with water with just this and then not bother generating all these, then a lot of energy is not going to be wasted. This is wasted energy in all these gaps here. And this band isn't so favorable. And so if you hit it here, then you can use the energy much more efficiently. So if you had something that's capable of being tuned, that is, you can tune it so that it hits just here, then you're good. Right? This is why I like microwaves. Microwaves are tuned to hit the rotation. That way we don't waste a lot of energy. It takes a certain amount of energy to rotate it. Too little does nothing. Too much does nothing. It just passes right through as if it were invisible. Does that make sense? Uh-huh.
What do you describe as telling us like this amount of water was absorbing these frequencies?
Yep. Right. Right. Actually, let me see if I can animate it.
Are we gonna have to, on the test, are we gonna have to do like harmonic motion?
No. Let me speed this up. We don't need the theory. Hopefully this shows the spectrum. Let me see if it shows the spectrum. Yeah, a little bit. So these are what we call these vibrations here. The symmetrical stretch, asymmetric stretch, bending. All right, this is a different kind. Now take that past one, that was called an absorption spectrum. This is also called an absorption spectrum, but rather than looking at peaks, we're looking at valleys. And typically in infrared spectroscopy, we look at the valleys. I don't know why they did it that way. They should have just flipped it. But this is what we call an absorption band. This is the big one. And now this one's flipped. So the other one we looked at, the higher energy was on the right. This one, the higher energy is on the left. And so you got to be careful when you look at these things. So I just look at the numbers down here and you can tell. And also they're not using meters. They're using something called wave numbers, which is more related to energy rather than wavelength. And so this is the high energy band here. And then we have these others. So we have the three bands corresponding to the three absorption of water vibrations. Then we can measure these. And so these would be the vibrations. Actually, this is, I don't know what this is then. The three bands would be, this one's two overlapping bands here. And so you have 1, 2, and then this is the third one. I thought that was the third one, but I was wrong. This is the third one here. So this is the bend. And so that's what those correspond to there. All right, so we're very interested in spectroscopy. Now, we do something called, in this lab, actually on Wednesday, we're going to do something called UV visible. In this lab, we're going to just do, I don't know what the spectrum is here. We're going to do a little bit of infrared, which we can't see, and visible, and a little bit of UV, I think, is in here. But you can't see that, unfortunately. And so we need a special detector. So we're going to do visible spectroscopy here. So this is emission. All right. Then where do you think plants are going to absorb? If plants rely on sunlight for energy, where is the most profitable place to absorb? Probably in the visible region. Right? And so let's take a look at this. That's an emission spectrum there. Let's take a look at some absorption spectra. I'll stop talking shortly. Actually, maybe I'll stop talking now. let's see, 10, 11, 50, 12. Oh, no, we have time. Spectra. Let's look at green plants. Now, green plants, are they emitting green light? No. Yeah, green plants, these are not emitting green light. Otherwise, at night, you would be able to see them. Are they absorbing green light? No, they're not absorbing green light either. And so they're neither emitting or absorbing green light. So what are they doing? Well, we can take a guess what they're doing by using the artist color wheel here. So we'll go red, orange, yellow, green, blue, and indigo violet are kind of overlapping. You know, because if we go back to the visible spectrum over here, you know, we go from blue and then it's kind of purple, but we're going to call that range indigo violet. So indigo violet's purple. So there's two ways that, or actually there's more than two ways we can make green. And this came up with the hunt for the blue LED. The red LED was known and the green LED was known. And you can mix red and green and get different colors. But in order to get all the colors in the rainbow, we needed one more, and that one more was the blue LED. With red, green, and blue, you can make any color you want. But one way we could do this is we could absorb red. If you absorb red, then the other colors will add up to green. And so if there's no more red in the rainbow, then the other colors combine to green. This is a quantum mechanical combination. I'll just call it combine. The other, we could absorb all colors. But green. Actually, I should have done that down here. Let me move this. So we'll put the artist color wheel up again. Red, orange, yellow, green, blue, indigo, violet. And in this case, we're going to absorb all the other colors except for green. Come on. Forget it. It's not quite working. There, I'll just leave it like this. So, so we're just left with the green here, but the absorption spectrum would look quite different. And so when we look at the absorption spectrum here, we're going to go from lower energy to higher energy. Let's see. Well, let me just check this. Yeah. So we're going to go red, orange, yellow, green, blue, indigo, violet. And so if this were the case, then what we'd see is an absorption band or peak around red, and then all the other colors would pass through. And so this is going to be absorbing the red light out of here. This would be the absorption spectrum, where this would be the intensity of the absorption here. Spectrum is singular. Spectra with an A is plural. And so these would be the two resultant spectra. The other spectrum would look like this. It would be red, orange, yellow, green, blue, indigo, violet, where we absorb the green. So there should be an absorption peak here. And this is removing the green light. Or some other combination. Some other combination would be something like this. What happens if we absorb indigo, violet, and orange? You know, then it should appear green, something like that.
With yellow and blue make green, huh?
Yellow and blue make green.
So you take the opposite of both those two and figure.
No. We're going to take these and then see how the other colors cumulatively add up, because the green is still there. So let's take a look at the solar spectrum of chlorophyll then, and see, or not this solar, we're looking at the absorption spectrum of chlorophyll. And so I'll go over here, and people have measured it. So over here, 760 would be our red. Actually, let me copy this. This is 650, 750, so about 760 here. This would be our red, orange, yellow, green, blue, indigo, violet. And so what does it look like for chlorophyll? It looks like it absorbs two colors, doesn't it? Yeah. And those two colors are going to make the other colors combine to a green. Okay. All right, so what are we doing today? We're doing experiment 4. Is that correct? Experiment 3. Experiment 3 is called atomic spectra. Let's take a break right now, and then I'll talk about atomic spectra when you come back. We'll take a 15-minute break. Have you done linear interpolation?
I think we're supposed to do that.
So, for example, what temperature did you guys get for the water, the gas, the water vapor? Did somebody get a temperature for that? Well, let's say I got like 24.5 degrees C. And so this is what we're going to do with something like that. 24.5 is halfway between these two. And so what I have to do is I have to figure out what is halfway between these two here. Oh. So I'm looking at this first chart here, vapor pressure, water at different temperatures. So we need the pressure of the water vapor, the water gas. And so let's say my temperature I read is 24.5, which is halfway between these two. What's halfway between these two? What I mean by halfway between these two is... It's still not on. Okay. Switched over. Okay. All right, just to repeat here, let me see if our recording's on. Yeah. So we're looking at the vapor pressure, but this comes in the full degrees. We measure to the nearest tenth of a degree. If I was at 24.0, I'd just read it off here. If I was at 25.0, I'd just read it off here. But what if I'm between these two? If I'm between these two, then I'm going to use linear interpolation. Linear interpolation is just saying if I'm halfway between 24 and 25, then I'm halfway between 22.4 and 23.8. And so that would be it. And so the way we set this up is like this. I'm 0.5 out of the total distance of 1. And so the first fraction we set up is 0.5 out of 1. This is halfway, is equal to x over what's the total distance here. Well, the total distance here is going to be 1.4. And so this is going to be x over 1.4. And therefore x is going to be 0.7. And therefore the vapor pressure correction of water is going to be 22.4 plus 0.7, which is going to give me 23.1. And so that's halfway between those. And so 23.1 millimeters of mercury. So you'd have to do the same thing if you're, 1/3 of the way or whatever. You set up ratios like this to determine that. Is that clear for this? All right, so that's for the vapor pressure of water table. You're going to have to do one. For the temperature correction table, we'll have to do a double linear interpolation. This is a bit more of a pain to do. And so what was the barometer? The barometer might not be at the same temperature as the gas. The barometer was calibrated at 0 degrees C. This is why we have to do this correction. If it was calibrated at 0 degrees C, what happens is it warms up to room temperature, the mercury expands a little bit. And we have to correct for the expansion of mercury. The expansion of mercury is going to depend on the temperature and how tall the column mercury is. The taller it is, the more, because it expands by a certain percentage. And so the bigger the correction is. And so let's say we were at, what was the temperature of the barometer? You measure the temperature of the barometer, it might not be the same, and it was also in a different room. So let's say the barometer was at 22.2 degrees C. And so that's in here, 22.2 degrees C. And then what was the reading on the barometer? Let's say the reading on the barometer was 759.3 millimeters of mercury. And so what we need to do is we need to figure out at 22.2 and 759.3, what is my correction here? Well, in this case, at 22.2, it's very close to 22. And so it should be very close to 2.7, right? Because halfway at 2.8, where would 2.8 be? 2.8 would be at 23. Here. And then at 759.7, we go from 2.7 to 2.7. So was there much of a correction there? No. So what we'll do is we'll just do a single interpolation. Whereas if it were two, did anybody get any other temperatures for the barometer? There's a thermometer mounted on the case of the barometer. So you can, what did you get? 25.0? You got 25.0? All right, let's go with 25.0. Let's see how we should correct it. So at 25, we're halfway between 24 and 26. So that means we're halfway between these. What was the pressure you got? 756.8. All right. So you got a pressure of 756.8. You got 25.0?
Yeah.
Okay. So we know we're halfway. Between these. And so this will make it simpler here. Halfway between these two is what? 3.1. So this will be 3.1 here. And then halfway between these two will be 3.0. Okay, and then we're at 750, what was it, 756? $756 well, let's. I'm just gonna make one. 756.1. So 756, we're over here. So what would you guess the correction is? This correction is not so precise. So what would you guess the correction is? 3.08. But we're not allowed that much precision. So we just say 3.08 would round to 3.1. So I'd just use a correction of 3.1. And so what you could do is you can eyeball it. But let's say I needed to do this precisely. If I needed to do this precisely, then what I would do is I do linear interpolation between here to get it. Well, this one we could do in our head because it's halfway. Linear interpolation here to get it. and then linear interpolation across here to get it. And so we'll just do the linear interpolation across. And so going across, I go from 740 to 756.1. So 740 to 756.1 is 16.1 out of a total distance of 20. 740 to 760 is 20. So my first fraction is 16.1 parts of the way out of 20. This is going to equal x, will take me here, out of a total of 0.1. And so this will be x over 0.1, which is the total distance across. And so we'll just calculate, solve for x. That's going to equal 16.1 divided by 20 times 0.1. And you're right, Tristan. X is equal to 0.08. And so this is 3.08. But we read the barometer only to the nearest tenth of a millimeter. And so we'll just round this to 3.1. And so that compensates for the expansion. So it's going to be 756.1 minus 3.1 millimeters due to the expansion of mercury, which is going to give us 753.0 millimeters of mercury corrected. So this would be the corrected barometer reading. You have to subtract it because it's due to expansion. So what you can do is you could just eyeball it, or you could do interpolations, because the precision, it doesn't change much, you know. It really doesn't change that much. And so you can kind of eyeball it and then get it, or you can be more precise and do it by interpolation. All right? For the corrections? Any questions on the calculations?
Where do we find this chart?
In the lab manual. It's in the experiment itself. I just took it out of the experiment. This is only if you use a mercury, you know, a barometer. But if you use something else, it's not. All right. Going back to the solar spectrum, since the sun emits all colors of light, we call it a black body emitter. So the sun is the black body emitter. And what we can do is we can go outside, and then we're going to use a spectroscope to look at it. When you look inside the spectroscope, it'll have, actually, let's go check one out, because we got to calibrate our spectroscope. And so, actually, we don't have fluorescent lamps anymore. Yeah, we can't calibrate our spectroscope. But go to the stock room and check out, everybody check out a spectroscope. So the sun, the sun consists mainly of what? What was that? Consists mainly of? Oh, I mean the solar spectrum? Okay, I mean compositionally, the sun is made up of mostly what element? Helium is the product of fusion, hydrogen. Mostly made up of hydrogen. And so it's emitting all this, what we call white light. White light is going to be all colors of the rainbow. When you combine all the colors of the rainbow, it just looks white. And some infrared and some ultraviolet. This is why you shouldn't stare at the sun too long, because the ultraviolet will cause some damage to the bonds. But what we're going to do is, the first step is we should calibrate this. And what are we going to calibrate this with? We used to be able to calibrate it with fluorescent, but now we switched to LEDs. And LEDs have more of a rainbow. So when you point this up at the LED, then look to the left. Do you see the rainbow of colors?
Oh, yeah.
Can you see all of them? Red, orange, yellow, green? Yeah. And so we're getting a pretty good spectrum like this. You know, it's emitting all the colors of the rainbow. And they're all kind of intense. Do you see any gaps in the rainbow? You don't really see any gaps. Does everybody see the rainbow? You have to look off to the left. And so that would be the spectrum. What we aren't getting is the intensity. It's hard. The intensity is how bright the light is. So some things emit more blue, some things emit more red. So for example, these emit more blue because they're a colder appearing, you know, brighter white light. Versus things that emit more red will appear warmer and less intense. But we can see that in the spectra, you know, and you can buy different lamps. Let me see if I'll just pull up some spectra for LEDs. And so that's the problem. These spectroscopes don't really measure intensity very easily. It's hard to measure the intensity. So here there's a little spike of blue here in the LEDs to give it more white appearance. We can compare it, like here's a warm LED. There's less blue here, more red-orange. And so it's a warm white LED. It's still white because you have pretty much all the colors in the rainbow compared to daylight. You know, daylight's going to have much more blue. So this is going to be appearing much more like daylight here. But we want this, you know, we want daylight sometimes. We like daylight. And so it'd be nice to make a light bulb that kind of mimics the solar spectrum, like this. And so what you can do is you can put some hydrogen in a tube like this. This is made out of quartz glass. And you don't put too much, because if you put too much, what we're going to do is we're going to put a little lightning bolt through here. And when you have a lightning bolt through air, what color is a lightning bolt? You know, what color light is emitted? Usually white light. But it's not going to be so easy, you know, if it's jagged like this. So what you do is you put low pressure. When you put low pressure, you can get a nice even lightning bolt. So there's hydrogen gas in this tube, and what we're going to do is we're going to connect it to, I think this is about 5,000 volt transformer. Yeah, it's about 2,000 to maybe 5,000 volt transformer. And then we're going to put a little lightning bolt here. And then take a look at the color here. So, ready? So I'll just switch this on. Does that look very white to you? It's going to be hard to see from there. It looks kind of over here. Looks like some white light in here. But if you look in the middle here, what color does it look like? Yeah, it looks like pink. It looks like phenolphthalein. And so this isn't a very successful solar lamp, even though it's made out of hydrogen. And so there's something weird going on with this. But anyway, what we're going to do is we're going to use this, and this is what it's going to look like when you look at it through your spectroscope. That pink color is a result of adding these four colors. This 656 nanometer red, plus this 486 green, plus this 434 blue, and this 410 violet. If we add up those four colors, then they appear pink. And we see no other colors being emitted. And so what we can do is we can calibrate our spectroscopes. We can calibrate our spectroscopes by holding this is the window where the light comes in, holding it to the middle of this, the pink part of this, and then looking for the 656 red line. What you're going to see is that you're going to see a sharp red line like this, and then what you can do is you could take a pen and then move this back and forth to calibrate it. But you know, you could do that later. This is going to be very qualitative because we don't have very many hydrogen lamps to calibrate. And so what we're going to do is we're going to look at making lamps like neon. I think we have a neon lamp, and we have a mercury lamp, and then we have a sodium lamp over here, which I'll flip on later. Sodium lamps are used in street lights, and they don't consume much electricity, but they give off an orange light. And then we're going to take a look at what what that looks like. And so what we're going to do is we're going to break up what we see with our eyes into the components of the rainbow that are emitted in this. And so this is just, you don't have to be very quantitative or very detailed. All we're going to do is this. We're going to measure all these lamps. We'll take a look at the LEDs, and then we'll go outside and take a look at the sunlight through this. Don't look at the sunlight directly, otherwise the UV is going to cause some damage to your eyes. But you can look at it through this here and then see if you see the full rainbow, which you should. All right, are there any questions? And so there aren't that many lamps, so just take a look. I think we have 2 hydrogens or 3 hydrogen lamps and various others. So take a look at all the lamps. But you're going to have to plug these in. When you plug these in, make sure it's switched off. And then plug it in. And then switch it on. Yeah, then you're going to use colored pencils and then just sketch it out. You don't, since these are uncalibrated, you don't have to be very precise with the measurements. Just get crude measurements. If we wanted to be a little more precise and accurate, we'd calibrate it with hydrogen first and then measure. But if everybody calibrates it first with hydrogen, it's going to take way too long.